Hello, everyone. Can those in the back hear me okay? Okay, great. Thank you. So welcome on behalf of the Earth Atmospheric and Planetary Physics group here at U of T. I'm really pleased to, I'm really pleased to have you here for the 2023 Nobel Lecture Series. This is actually a pretty special year for us. This is our 20th anniversary since we started the lecture series. This is quite remarkable. The lectures here began in 2003, and they've been made possible by the Reginald and Muriel Nobel Fund. And so before John Paul Mastrogiacomo, who is a member of the Nobel Lectures Committee, introduces our speaker for the week, I'd like to say a few words about our benefactor, Reginald Noble. So Reginald Noble was born on a farm in Clinton, Ontario here in 1911. And he did a bachelor's in honors math and physics at U of T in 1934, followed by a master's degree in physics, specializing in meteorology, also here at U of T. He then moved on to the Meteorological Service of Canada, where he had a fairly illustrious career, eventually becoming assistant deputy minister. Before the war, he was posted to Newfoundland in 1937 and was officer in charge of the new district aviation service in Montreal and established a weather forecast office in Halifax, all before age 30. Between 1940 and 1946, during the war, he was in charge of a program seconding almost 400 newly trained meteorologists to Royal Canadian Air Force bases, and he was the meteorological advisor to the RCAF Chief of Staff. After the war, he moved to Toronto and played an important role in an era of rapid growth at what we now call Environment and Climate Change Canada, including the move to the building at Downsview that many of us are familiar with. Reginald Noble was known as a highly skilled administrator, quiet and full of common sense. He was keenly interested in science and the happenings here at the University of Toronto, and we believe that he must have enjoyed his time here in physics, as he left us a very generous endowment for the Atmospheric Physics Group, which has allowed us to establish this lecture series, including the bi-weekly seminar series as well. So we're all extremely grateful to Reginald Noble for his generosity and making these lectures possible. And so I'm pleased to have John Paul introduce our speaker for this week. We have a lovely set of lectures, and I hope many of you will attend in person, and I look forward to seeing you over the course of the week. So thank you.
Thank you, Professor Jones, and thank you all for being here. It's a great pleasure to introduce our speaker, Dr. Anne-Marie Eldring. Dr. Eldring earned a Bachelor of Engineering from the Cooper Union for the Advancement of Science and Art in New York City. She then earned a master's and PhD in environmental engineering science from the California Institute of Technology. Following her education, Dr. Eldring was an assistant professor in civil and environmental engineering at the University of Iowa, where she worked in developing a research program on air pollution. Then in '99, she returned to Caltech and joined NASA's Jet Propulsion Laboratory, where she worked until 2022. At JPL, she worked on a number of satellite missions. Until 2011, she was the deputy principal investigator for the Tropospheric Emission Spectrometer, which was launched on the Aura spacecraft in 2004. Then Dr. Eldring served as the deputy project scientist at the Orbiting Carbon Observatory 3 and the project scientist of the Orbiting Carbon Observatory 2 and 3. For her role in these satellite missions, she was awarded the NASA Group Achievement Award in 2005, 2007, 2013, 2014, 2016, and 2018. She was also awarded the NASA Outstanding Public Leadership Award in 2017. In January of last year, Dr. Eldring retired from JPL, and since November, has been at the National Institute of Sciences, Standards and Technology, participating in their greenhouse gas measurements program. At NIST, she's working to coordinate with other federal agencies and the research community to enhance the connection of new and future satellite measurement of greenhouse gases with internationally recognized standards. Please join me in welcoming Dr. Anne-Marie Eldring.
All right, thank you so much for that introduction. And if you can't hear me in the back, just wave because I'm wearing a walk around mic and it might not be perfect. Thank you so much for that introduction, and thank you also for inviting me here at Toronto. It's really fun and enjoyable to come and meet with new groups of folks, talk to students, postdocs, and new staff members. Enjoy a beautiful spring day. But I have to say, I got a little extra mileage out of the Noble Lecture Series because I have 3 big brothers and they never seem to think I've amounted to much anything. So I told my big brother, hey, I got invited to give the Noble Lecture Series. And he looked at me like, what? And I waited a few seconds and then I said, at the University of Toronto, we're not going to Europe. So I appreciate that. Gave me a little cred with my brother for a few minutes at least. All right, let us proceed. And you may need to put your seatbelts on. We're going to have a little fun run here. Where I want to take you today is talk a little bit about climate change and greenhouse gas, probably a topic you all know, but just want to set the stage a little bit. And then the carbon cycle in particular, what we know, what are some of the big questions, and then why is it we went to space and how can we actually measure carbon dioxide from space, and a little tilt looking to the future, some of the new exciting things that are happening, as well as things I'll talk about later in the week. So let's just get going. All right, I might not be able to get that thing to go away. Let's see. No. Oh yeah, okay, let's try that. I'm almost an AV expert, but not complete. There we go. All right. So greenhouse gases, you're all familiar with the effect of greenhouse gases. You can think about it when your car sits in the sun and it gets so hot inside, right? It's why does it get so hot in there? Well, you've got radiation that gets in through the windows, visible wavelengths, and then this heat, the infrared wavelengths, can't get back out that well. So things get super heated up. And that's sort of what's happening to our planet. These gases serve as a little blanket. They trap infrared radiation. And a nice blanket is nice, but if you put on 3 blankets on a summer night, it's a little bit more than you want. So we're adding greenhouse gases, adding this capturing of infrared radiation. It's driving the heating of our planet. And there's many gases that have these behaviors: methane, carbon dioxide, chlorinated fluorocarbons. But the carbon dioxide is the most important one that we as humans are releasing. So I'll spend a lot of my time talking about carbon dioxide. We'll do a little bit of methane discussion as well. And in terms of the measurements of carbon dioxide, Charles Keeling is a name that may be familiar to you. He started measurements in Mauna Loa in Hawaii. He was an oceanographer at the Scripps Institute in San Diego. So back in '58, he started making these measurements that have now become part of a record operated by the US agency NOAA that track the carbon dioxide measurements. And I'll tell you a little more about the details. So Keeling was the man who started this. His son is actually active researcher now, taking over some of this work. So this is a Keeling curve. It started a little bit before I was around 320 parts per million and grown up to 420. You'll see 2 curves on this figure. The red one that's going up and down is the monthly average, and then there's a black line that's deseasonalized. So you just see the growth in that. You can grab data online if you ever want more details. And the numbers, I'll have a few numbers I'm going to try to get you to get in your head. 2 to 3 parts per million growth per year is the change that we're seeing in carbon dioxide. So let's talk a little bit about these wiggles and the growth. So what are those wiggles all about? And 420 is a number for your head. So 420 is about where it's at these days. Remember, it started at 320 when I was born. So there's 100 part per million change. Almost a quarter of this increase has happened over just my lifetime. That's kind of a wow. So what's this wiggliness? Well, plants are actually a really important part of the carbon cycle. In the spring, the leaves are growing, carbon dioxide is being drawn out of the air. So we see a reduction in the regions of the world where these trees are. In the summer, continued removal of the carbon dioxide. And then in the fall, the trees are shutting down, the leaves are falling off, they're starting to decay. And in the winter, we really don't have this photosynthetic activity. So you have this big kind of breathing of the earth through the plants that's driving that seasonality over the year in the carbon dioxide record. But we also see this increase over time. So we have to look at a few pieces of this system. We've got emissions, we've got oceans, we've got trees. They're all playing a role in this, in what we find. And I want you to think about two different concepts I'm going to use. One is exchange. So we mentioned those plants take out carbon dioxide and then release it. So that's an exchange, like a huge amount gets taken out by the plants and then it gets put back in. So if exchange was balanced, there's in the net no change. The net exchange is, well, what if I took in a little bit more than I put out? In the net, I would be modifying the balance. So those are a couple of terms I'll use as we talk about the carbon cycle. So emissions from fossil fuels are a key part of our carbon cycle. We burn oil, gas, and coal. This is a time series that's showing you from 1990 up until 2022 projection, what the emissions were. And a couple things to take away here. Unsurprisingly, these emissions have been growing, although there's periods of drop, like the global financial crisis in 2008. COVID, you probably all know, had a big impact on what we were all doing and therefore a big impact on emissions. So they've been growing, but the rate is maybe not as large as it's been in some past decades. And a number for you is 37.5 gigatons of carbon dioxide. That's the total amount. It's pretty well known because gas and coal and oil are traded and sold and shipped. So we track that stuff. So we know pretty well what these emissions are. Now, the oceans are an important player. You may not think about this, but all of that water in the ocean dissolves carbon dioxide. And there's a huge exchange. So 290 gigatons of carbon dioxide are taken up and released each year. Different parts of the ocean behave differently and the water temperatures affect it. But there's a little net change. So they actually take up 10 gigatons more than they release each year. So you're in net taking extra carbon dioxide into the oceans. And the number I'm giving you here is estimated with global ocean biochemical models and some observational data. And the figure on the right is just showing you different types of estimates to give you an idea of how well we know this or don't know this. So it's a bit more uncertain, but we think about 10 gigatons of carbon dioxide. And similarly, the trees and the plants are helping save our bacon, right? When they take up and release carbon dioxide, 500 gigatons a year, but in the net, they take out 11 more than they give up. So they're a place that's taking in carbon dioxide over time, about 10 gigatons of carbon dioxide. This estimate, and this comes from a vegetation model where people are trying to model all of the different processes that happen and make sense of observational data that we have. So there's, reasonable science behind these estimates here. So plants, trees, oceans, and then one other area we think about is land use change. So this is where we're trying to capture what's happening because of deforestation or draining of draining of soils that have a lot of organic stored carbon, as well as regrowth. There's parts of the world on this lower left, you can see the red is where you tend to be removing carbon and the green is where you're having additional uptake of carbon. So there's forests that are growing back after harvest, agricultural abandonment, et cetera. So in the net, we think that the land use changes are adding about 4.5 gigatons of carbon dioxide per year. So we can use this to put together a budget. This figure kind of showing you the flows, that fossil fuel emission, land use emission, uptake by the plants, uptake by the ocean. There's also huge reservoirs of carbon in our earth between the gas and the coal, and the oceans themselves store huge amounts of dissolved carbon. So this is kind of the big wrap up picture of the carbon dioxide. And a nice way to try to think about this is we burn fossil fuels and we change things we do with the land to release about 40 gigatons. Fortunately for you and me, about a quarter of that, what we've released gets taken out by the oceans, about a quarter gets taken out by the land, and only half of it ends up in the atmosphere, because we would really be cooking if the land and ocean didn't take some of that extra carbon dioxide out. So that's our picture for things in the last 10 years about what's happening with the carbon cycle. So you might think, well, what are you talking about? We have a picture, we got a budget, so we're good to go. Well, if you think about the past, this is 1850 to today, a way to picture what's happening in the carbon budget. And that growing gray line is our increased uses of fossil fuels and emission of carbon dioxide. The orange is the land use part of it. And then the bottom of the graph is where it all goes. So there's a bit going to the atmosphere in the bright blue, some going to the land, and some going to the ocean. So we've tried to put together a picture of the past and what happened to our carbon cycle. You can see that the emissions are growing and the uptake by land and the oceans has been growing. But do we know that's how it's always going to be? We try to make projections of the future, and this is a figure from the IPCC report, and it's showing you what people predict land uptake is going to be. So in 2050 and 2100, some folks are predicting it just kind of flattens out. Some say, oh no, it's going to really take up a lot more. And other models are saying, no, the land is going to kind of become exhausted and not be able to take up more carbon dioxide. And the low model agreement is shown in the hatch to that figure. So they don't know where it's going to happen. They don't know exactly what sign it's going to be. So there's a lot of uncertainty about the future and how carbon cycle might evolve. And that's what's tricky when you want to try to make good predictions about climate change and the future of our planet. And even the annual growth rate has been hard to make sense of. So I've got the Keeling curve again on the left, and then the blue bars is showing how much extra carbon dioxide in part per million showed up each year. So we see that the growth rate averaged over 5 years, those blue bars, or 10 years, is kind of bouncing around. And you also see every year is quite different from another. You had a year back in the 1985 where you had 2.5 part per million growth, and then a few years later it was only less than 1. So there's huge variability, we think, driven by things like El Nino, southern oscillation, droughts, heat waves, cold summers. All these variability factors probably feed into that, but we don't really understand it in great depth. And in addition, if that wasn't enough of a mess, we've got this picture of the carbon cycle, but I've only told you annual average integrated numbers. What happens if you try to say, well, what's going to happen in Southern Africa versus what's going to happen in Northern Europe? Again, more uncertainty and disagreement. There's a lot of spatial variability. We talked about plants taking up carbon dioxide. Well, they're not in the oceans. They're in primarily the Northern Hemisphere is a very active area for that. You have different kind of processes that control things in the Southern Hemisphere. So there's a lot of spatial complexity. So how can we learn about this? How can we get the information we need to do the science that we want to do? So that's what I want to kind of dive into in the next bit of this. But one more number to get in your head. So we talked about 420 part per million is the current concentration. And we talked about, we add about 40 gigatons of carbon. So when we want to make a measurement, you might say, well, 1 part per million, I can do that with my instrumentation. But the problem is, if you're trying to find a gigaton of carbon, you need to find 0.13 parts per million. So the size of the quantities we're interested in, which are 1 or 2 gigatons probably, only change atmospheric concentrations by fractions of part per million. And that's where this gets kind of tough sometimes with the observations. So we'll come back to that in some of my discussions about the satellites. So back in the day, people built models to try to understand the carbon cycle. Folks who, like me, who actually published our first paper with graphics that you had to draw on PMT paper. Remember representations like this of models. When I did my PhD on air pollution, the computers were one of the limiting factors. You couldn't run a 3D global model and include aerosols. It just didn't happen, people. So things are a little bit simpler, but in some ways our model processes represented the best you could do with also the observational data you have. Here on the left is the NOAA network. That's actually the international collaboration, including the NOAA data, showing where we've had long-term carbon dioxide measurements, as well as some campaigns with ships, et cetera. So if the left map is the data set you have about carbon dioxide concentrations, you can learn something about regional flows. You can probably figure out Northern Hemisphere interchange, but there's a lot of parts like the oceans are very poorly sampled. South America, Africa, very few data sets. You see Australia's only got one measurement there. So there's limitations in the coverage of this data. And on the right, I've just Dave Chris took a model field and then sampled it the way that network would see. So this is, for example, what it might look like in January. And then if you go into March, you have some drastic changes in certain regions. And then in July, it looks even more different. So how do you make sense of what you see with all those changes if you have limited view of the world? So that's kind of the quandary. One thing about this network, it is very precise. So I mentioned how you want to see changes of maybe 2/10 of a part per million to understand some exchanges. Ground-based networks are, they work in that realm. But scientists being scientists, let's try something new. So satellite is a new way to try to think about carbon dioxide. And as was mentioned in my introduction, I had gone to JPL in the 90s and we were working on air quality measurements from space. I have to say, I remember when people saw us getting ready to do our experiment and they were like, you're crazy, it's never gonna work. How can you see ozone and different layers of the atmosphere from space? But it worked. Carbon dioxide, the same thing. How are you going to find 1 part per million of carbon dioxide from space? It'll never happen. Let's just say it didn't happen the first year, but it happened eventually. So it was a very fun time. This proposal to do these measurements started in the 90s at JPL with collaborations and a whole number of scientists. And we got this instrument built. The bad news is the first time they tried to launch the Orbiting Carbon Observatory, there's a protective cover on the rocket called the fairing, and the fairing did not explode and fall off properly. So that never made it to space. It fell back down in the ocean. Some people with bad sense of humor call that one the Ocean Carbon Observatory. Yeah. So I joined the program in 2010 when they started to rebuild for the next one. So you'll see this OCO-2 in a lot of my stuff, and that's because it was a second build. Fortunately, it successfully launched in 2014, and I think a number of the folks here were even able to come and see that happen. So we got this instrument in space in 2014. The figure on the left gives you an idea. We fly around the Earth about 15 times in a day to make a measurement. We're not mapping the whole Earth. We're not in a geostationary or staring at it. We're just sampling a bit of the Earth, 10-kilometer wide swath. The game plan was to try to get a part per million accuracy. And we managed to get about 100,000 measurements per day of carbon dioxide. And I'll show you some more pictures. On the right is sort of if you imagine the world as a complex place and over 16 days, you sample a lot of that, it still exaggerates the spatial extent of what we managed to see with these measurements. So this is the idea. Let's measure it from space and try to get that global picture. It's going to be less precise, but we'll probably learn something from it. And how might we do that? Well, we look at reflected sunlight. So those are the wavelengths we use. And there's 3 bands that we use shown up there on the kind of bar graph spectral looking thing. We have an oxygen band, and that's great because it's very sensitive to clouds. It's kind of at a wavelength your eyes see. And then we have 2 specific places that we measure for carbon dioxide. One that's only weakly absorbing and one that's more strongly absorbing. So there's a 3-band spectrometer. We get about 1,000 spectral points across each band. Those figures on the bottom there, just kind of showing you the instrument layout, kind of looks like a V6 engine to some people, but you've got 3 separate spectrometers almost locked together to get those 3 channels. And I'll say more in later lectures. If you have a chance to come, I'll get into a little bit of the details of that. So we got those missions into space and actually started collecting measurements of carbon dioxide. And this is just some snapshots of maps we've made. On each of these figures, there's a full month of data with cloud screening applied, data corrections applied, and footprints exaggerated. So again, overstating what we actually see, but you couldn't see much if I didn't do that exaggeration. And one thing to highlight here is we have fall data, so November, fall. And when I use seasons, I'm always talking about Northern Hemisphere way of seeing the world. So fall season, and then the early summer in the lower figure. And you can see this scale is actually covering 25 parts per million. So from 390 to 415. And just from the colors, right? The blue in the 1 is a much lower concentration. You're starting to see green in the summer, although there's a blue bit up in the Northern Hemisphere. So I'm just going to kind of step through a full year of data and talk about some of the really obvious things we see in the data when you make these measurements from space. So this is the start of the September into November. A pretty blue. Northern Hemisphere is actually a little bit lower concentration than the Southern Hemisphere. And as we get here into November, October, November, and then November, December, you almost see more uniformity across the globes. One of the other things you might note is that as the seasons change, the sun availability changes. So these band of measurements is going to slide up and down north and south just because of the sunlight that we need to reflect. And then we get into the winter time, and you'll start to see a little bit of warming in the colors of the Northern Hemisphere. So what's going on there? Why is January, February more concentration of carbon dioxide? Well, our heating's still on, we're still driving around, we're still burning those fossil fuels, but the plants aren't really active. So that constant carbon dioxide is just building up in the Northern Hemisphere as we go through the winter. Here you see into March, April, still just getting a bit warmer and warmer. And now spring is going to come pretty soon, not quite yet. Again, still yellow into a little red. And now suddenly as we get into June, you see a little more bluish feeling. And then here in June into July, you really see that plants have turned on. They've started taking that carbon dioxide out and really just changed everything in the Northern Hemisphere. And then by the time you get into October, it's just really obvious. So that breathing, that seasonality driven by the plants, very obvious in this data. As we get here into September and then November, again, that starts to fade away. And I think what I wanted to do on this one is just starkly contrast. This is September into October 2016. So you're looking at greens and blues, and just 1 year prior, that same months, much more in the blue. So that's that growth rate, 2 to 3 parts per million. The whole color bar is kind of shifting as you go from year to year. So this was some of like overview of what we have in the OCO2 data. And then some point in my lectures, we'll talk about OCO3. And OCO3 has this great way of mapping out regions of the world in 2 minutes. This shows us flying over LA and looking at the carbon dioxide over the city. You can collect 4 stripes of data, and you can just see there's parts of the city that have a much higher concentrations than the more outlying areas of the city. It's a new way of looking at carbon dioxide that's been really interesting and valuable to try to get some of this urban enhancement measurement. So that's just kind of highest level what we're seeing from space with our data set. But I would be remiss if I did not talk about some of the other important work we have to do. So I might go out there and measure carbon dioxide and tell you, wow, I found 416 parts per million over Los Angeles. But a lot of the science community is going to say, so what? How does that relate to any other information I have? So we have standards, we have reference data, So we have a whole program to tie what we measure from space back to the reference data. And the TCON network, which you've probably all heard about by now, is a core part of that. So they have, there's in situ sampling that's tied to the WMO, or the internationally recognized scale. Those aircraft or air corps overfly the TCON, the satellites overfly the TCON, and we try to relate the data to each other. And a lot of what we've done through this program is with this amazing network that's across the globe and continually growing. And we sample TCON sites with our different satellites. That lower figure is showing you about 20 by 20 kilometer scale of the data we collect, a lot of aggregation of that data, as well as analysis of time series, seasonal cycles, et cetera, et cetera. We could give a whole lecture on this. And I have to acknowledge Deborah Wunsch and the whole TCON crew, because if we didn't have that community of scientists, our OCO2 and OCO3 experiments would really have little value in the science world. So the TCON work is just really, really important to what we're doing. So thanks, Deborah. So did we do any science with this data? Well, not me personally, but we have a whole community of people. And I just want to tell you a couple of the science stories of what we found by measuring carbon dioxide from space and going back to this question about the carbon cycle and how the future might unfold. So we were sort of lucky. We launched in 2014, and 2015, 2016 was a big El Nino period. So when the El Nino happens, you tend to have drier, hotter conditions in many regions of the world. And often the conversation has been, well, El Nino happens, places are warm and dry, and it looks different. Well, with the OCO2 measurements, we started to really differentiate. We could see something happening in South America that was different from Africa and was different from Indonesia. And this is at the highest level in analysis about the carbon exchange in those three regions and how it compared to other years. So we saw more carbon released or less carbon taken up in all three regions of the world in this El Nino period. But what was even more interesting was that we could learn why that was happening. And it's not the same reason for every region of the world. There was less photosynthesis in South America because it was really, really dry. Whereas in Africa, it was very hot and the litter was decomposing more rapidly. And in Indonesia, we have fire. So we now learn more about what's happening in different regions of the world that wasn't possible before. And it gives us some food for thought. So what does that mean for the future? If we're in a warmer, drier world, do we learn something about how the carbon cycle might respond by what we see in these regions? So this was kind of one of the first findings that came out of these experiments. And there's a lot of work still underway. These are just some snapshots from the EOS magazine. For example, there was a big fire season in Australia, 2019, 2020. So you can learn about how much carbon was released through these fires. There's also work around crops, and there's this whole other piece of the mission I'm not talking about with solar induced fluorescence and plant behavior. So folks are trying to understand how they can learn about crops, crop productivity and carbon flux anomalies with these missions. And then if you come around on Friday, I'll talk a little bit more about the global stock take and just efforts to try to use these measurements in a larger program of analysis to make estimates of carbon flux from different countries and how that fits into our larger policy discussions. So there's a lot happening, and I could, again, show you, I will show you more examples of the different kind of analyses people are doing. But the fun's not all over. So folks like you, especially students and postdocs, it's a really amazing time to be in this business. So I got to be part of the OCO2, OCO3 mission, but there's more stuff coming online. The Japanese actually launched missions before our NASA mission, and they continue to just move along and put new assets in space. The next one's going to be GOSAT GW. The Europeans have microcarbon development, which should launch in a few years. The CO2M mission, which I'll talk about in one of my other lectures, is if executed as promised, will be an amazing step forward in carbon dioxide measurements with a focus on human emissions, fossil fuel emissions, including aerosols, nitrogen dioxide. So there really is going to be an amazing set of data. But we do have challenges with this. The more measurements you get, the more you have to figure out how they relate to each other, how they tie to the standards, how to actually use them in your analysis. So it's an exciting time for carbon dioxide. And if you're paying any attention, you probably know methane is also a great interest these days. In the news feeds I get, it's like an article every day about something related to methane. And there's a lot in space and there's a lot to come yet. So there's going to be, again, tremendous amount of data related to methane, both kind of global type measurements as well as point measurements. And people are troving back into the older data sets. These are just some examples of how imagers put up for a different reason have been used to find methane plumes. Worldview 3 is on some of these figures, and then Prisma is another imager on the space station, finding stuff from oil and gas, finding things from coal mines, just amazing information coming out on methane from even just satellites that happen to have some sensitivity. So I'm going to wrap it up there so we have a little time for conversation and questions. But what I've tried to get you warmed up to is that satellites are really been an amazing tool to add to our knowledge about carbon cycle, concentration of climate gases. But using that data with ground-based data with an explosion of new satellites is going to be a challenge, I think, in the future, and relates to the work we're doing at the National Institute of Science and Technology, as well as work like the TCCON network has been doing. It's a really exciting time. There's new satellites going up. There's new interest in methane and plume finders. And one of the things that I think about more and more is how do we make that data useful to people? So not just into our science world. And the methane plume finders, some of them actually have strategies built in to feed information to producers, to regulatory groups, et cetera, et cetera. So there's growing connections in that, but it's still an area of development. So it's an exciting time we live in, a lot of opportunities in science and science related to policy. And thanks again for your time and attention. Let's have some questions. Thank you.